Welcome to reading.com. In this video, I am going to explain what is restore division and its circuit diagram, algorithm flowchart with some example problems. Binary division is similar to normal decimal division. The only difference is the involved numbers are only zeros and ones. We know that the division operation involves the two operands called dividend and divisor, and we get the two results called quotient and remainder. We can express the division operation in another way like this. If you multiply the quotient and divisor and add with the remainder, we can get the dividend. This division operation is achieved by two different types of algorithm. One is called restored division, another one is called non-restored division. In this video, I am going to explain what is restored division. This is the circuit diagram for restored division algorithm, in which the important components are Q register, which contains the dividend value, then B register, which contains the divisor value, then A register, it contains the remainder value, then arithmetic and logic unit, sequence counter, it helps to repeats the operation in n number of times, then shifting can be done by the shift register. These are all the important components present in the division circuit. Let's see the circuit diagram deeply. Here, A and Q registers are two separate registers, but they are arranged in a serial manner and treated as a single register. That means when we do that shift operation, the content of the both the registers are involved. We will see it in the example problem. Let's conclude the initial stage of the division operation. So when Q register contains the dividend value, B register contains the divisor value, A register contains zeros initially, then sequence counter contains the n value. N value is nothing but if we divide the n number of bits, for example, this circuit is particularly for the 32-bit division operation. So sequence counter is resetted as 32. And one important thing is, if the divisor value is 32-bit number, we can include the one more bit called sign bit. In the same way, A register also contains one extra bit called sign bit. So for this sign bit operation, your normal ALU contains n plus 1 bit adder. So this is the initial condition. At the end of the division operation, your Q register contains the result, that is quotient value. Your A register contains the remainder value. So this is the circuit diagram of the division operation. Let's move to the algorithm flowchart. This is the algorithm followed to achieve the restore division. So before this algorithm, I want to explain one simple logic of division operation. This restore division operation is nothing but some modification in the adder and subtractor circuit, in which quotient can be calculated by how many times the divisor subtracted from the dividend, and the remainder can be calculated by the final value that is less than the divisor. Let's see the example. If you want to divide 10 by 3, then 10 is the dividend and 3 is the divisor. Initially, quotient is set as 0. First you subtract the dividend minus divisor, you can get 7. You can check whether this is the positive or negative value. This is the positive value, then you increment the value of the quotient. So initially quotient is equal to 0, now it becomes Q equal to 1. Then repeat the subtraction operation. 7 minus 3 you can get 4. This is another positive number, so increment the quotient value. So Q becomes 2. Then repeat the subtraction operation again. 4 minus 3 you can get 1. So this is also a positive value. Then you can increment the Q value, that is Q equal to 3. Then you again perform the subtraction operation. Now you can get the negative value. So you stop the increment process of the quotient. Now then you can restore the value. Restore means you can add the 3 again. You can get the old value, that is called restoring. then you can get the old value 1. So this old value is less than the divisor value. So that is called remainder. Then quotient is incremented from 0 to 3. So now the quotient is 3. I hope now you understand the meaning for the quotient, how many times the divisor is subtracted from the dividend, and the remainder is the final value less than the divisor. When we do the repeated subtraction operation, we can find the quotient value, that is how many times the subtraction can be possible. From this result, this is less than the divisor value, so 1 is the remainder value. So this is the logic behind the restore division operation. Let's we move to the flowchart. So in this flowchart, first part is giving the initial value. A register contains zeros, B register contains divisor value, Q register contains dividend value, sequence counter contains the n value. N value is nothing but number of bits you are going to divide. For example, if you are going to divide 32-bit numbers, then the n value is 32. But in this example, we are going to discuss about 4-bit number. So we are setting the sequence counter as 4. So this is the initial value. So in this circuit diagram, we already discussed what is the initial condition for all the registers. So this is the first thing. Then we have to shift the content for A and Q register in the left position. That means A and Q register are treated as single register. We have to shift the element from the left. So this is the meaning for the shift left of A and Q register. Then you have to do the subtraction operation. A minus B, that is B register content can be subtracted from A register, then the result can be stored in the A register. So we have to do the subtraction operation between these two register contents. Then finally we can put the result in the A register. So this is the meaning for this operation. Then after the subtraction, we have to check the sign bit of the A register. So in this circuit diagram, we have special extra register used for the sign bit. So after this subtraction operation, we have to check the sign bit of this register. One more important point. Once you do the left shift operation, so an value can be left out, an minus 1 value can be shifted here, an minus 2 value can be shifted here. In this way, every element can be shifted in one position and the q0 value becomes empty. So after shifting operation, we have to do the subtraction operation. After subtraction operation, we have to check the sign bit of the A register, that is this value. If this value is 1, you can set the q0 value as 0. If the value is 0, you can set the q0 value as 1. So this is the algorithm given in this flowchart. So I repeat again, if the sign bit of A is 1 means you can set the q0 value as 0. If the sign bit of value is 0 means you can set the q0 value as 1. If it is 0, you can do the restore operation. Restore operation is nothing but reverse process of this subtraction. You can add the B value again, you can get the old value, that is called restoring. So after restoring, you can decrement the sequence counter value. Initially, if the division operation involves 4-bit number means sequence counter value is 4. Then after the first iteration, sequence counter value becomes 3. You can check the sequence counter value is 0. You can repeat this operation again. You can again do the shift operation, then do the subtraction operation, check the sign bit of the A register value. If it is 1, you can put the 0 in Q0 position and do the restore operation. If it is 0, you can put the 1 in Q0 and don't do the any restore operation and repeat the operation again. So this is what present in this flowchart. Let's we see this operation using some example. I am going to explain this division operation using 4-bit number. So when the problem is given, you can try to write the dividend and divisor both in the 4-bit number. So here the dividend is 10. So I can write the equivalent 4-bit number of the 10 is, that is 1010. And divisor is 3, that is 0011. You can add the sign bit also, that is 0. If it is a positive number, so this is 0. And you have to find the 2's complement for 3. Because we are going to do the subtraction operation. Subtraction operation is nothing but if you want to minus 3 from A register content, you can add the A register content with the 2's complement of 3. That means minus 3 can be represented as 2's complement of 3. So if you want to do this operation, you need to find the 2's complement of the divisor. So this is the 2's complement of the divisor that can be calculated including the sign bit. So the 2's complement of 3 is 11101. That means this is minus 3. So if you want to perform this operation, you can add the A register content with this value. Let's work out the example problem. So first you have to write the A register here and Q register here. I already told that these two registers are treated as a single register. Initially A register value contains 0. So I put 0 here including the sign bit. And Q register contains the dividend value. Here the dividend value is 10. 10 can be represented as 4-bit number 1010. And the divisor value is 3 including sign bit, that is 00011. That cannot be represented here. When we do the subtraction operation, we have to use the divisor content in B register. So initially you have to write like this in your answer script. So this is the sequence counter value. Here we are going to perform the 4-bit division operation. So the sequence counter value becomes 4, that is represented as 100. So this is the initial value done. Then we have to do this operation. That means shifting the content left in the A and Q register. When we shift the register in left means this 0 becomes left out. You can write these 40 value here and shift the 1 into this position, then shift the 0 here, shift the 1 here, shift the 0 here, and Q0 position. This is Q0, Q1, Q2, Q3. This Q0 position becomes empty. So this is the meaning for the shift left of A and Q. So we have to achieve the shift left of A and Q register. Then we have to do the subtraction operation. So when we subtract the value, you can write the 2's complement for the divisor value. So we already discussed about the 2's complement for the divisor value. So I am going to add 2's complement for the divisor, and this is the result. 1 plus 1, 10. 1 is here. So 1 plus 0 plus 0, 1. 0 plus 1, 1. 0 plus 1, 1. 0 plus 1, 1. So this is the subtraction operation, that is A minus B. So in this algorithm, A equal to A minus B is done. Then we have to check the sign bit of the A register value. If it is 1, you can put the 0 in Q0 and do the restore operation. If it is 0, you can put the 1 and no need to do the restore operation. You can repeat the next iteration. Now we check what is the sign bit of A. So after subtraction, I can get the sign bit of A is 1. Then I am going to put the 0 in the Q0 position. Then I do the restore operation. Restore operation is nothing but add the B register content. So B register content is the divisor value. So divisor value, I can directly write the divisor value and add these two values. 0 plus 1, 1. 1 plus 1, 10 carries 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 1. You can ignore this extra bit. So this is the final result. So this values become same as this value, that is after shifting operation. That means we are achieved the restore value. So this is called first cycle. So the first iteration is over. So we have to decrement the sequence counter value. So the sequence counter value becomes 3. We have to repeat this operation again up to sequence counter value becomes 0. So I am going to shift the A and Q register value in the left position again. When I do this shifting operation, this 0 becomes is left out. I can write this 0001 here and shift the 0 here, shift the 1 here, 0 here, 0 here, and I have the blank value of the Q0. So the shifting operation is over. Then I have to do the subtraction. So subtraction means I can use the 2's complement for the divisor. So I can add the 2's complement for the divisor. So after adding, I can get this value. I can check the sign bit of the A register. So this is 1 again. So I can put the 0 in a Q0 position and do the restore operation. I already told restore operation is nothing but adding the actual divisor value, you can get this old value. So this is the second iteration. In the second iteration, you can decrement the sequence counter value. So before that, the sequence counter value is 3. Now the sequence counter value is 2. So second iteration is over. You can repeat this iteration again. That means you have to do the shifting operation. So when I do the shifting operation, this 0 can be left out. I can write 0010 here, 0010, and shift this 1 into this position, shift this 0 into this position, 0 into this position, 0 into this position, and left the Q naught value. Then I do the subtraction operation. That means adding the 2's complement value, I can get this value. I can check the sign bit of A register. Now this value is 0. So I can set the value in Q naught as 1. Now I no need to do the restore operation because I am getting the sign value 0. You can check the algorithm. If your sign bit is 0 means you can set the Q naught as 1. You no need to do the restore operation and do the next iteration. So now the sequence counter value becomes 1 from this 2. So now I want to do the shifting operation. So this is the A register content. So I want to remove this 0. Then I am going to write the 0010 here, 0010. Then I shift the 0 from this position into this position, 0 into this position, 0 into this position, 1 into this position, and left blank as the Q naught value. Then I am doing the subtraction operation. After adding these two value, I am getting this value. So I am again get the sign bit of the A value is 0. So I am setting the Q naught value as 1. I no need to do the restore operation. So now the sequence counter value becomes 0. I can stop this iteration because this is a 4-bit number. 4 times I am doing this operation. So finally I am getting the Q register content as quotient, and the remainder value can be stored in the A register value. So this is the given problem, that is 10 is the dividend and 3 is the divisor. When we divide this 10 by 3, I can get the quotient as 3 that can be present in the Q register. Then the remainder is 1 that can be present in the A register. So in this way you have to work out this problem in your examination. Let's you try this another example, that is 9 divided by 2. Here 9 is the dividend that can be written as the 4-bit number 1001, and divisor is 2 that can be written as 0010. You have to include the sign bit. This is positive number. You have to include the 0 for this. Initially you also find that 2's complement for this divisor, that is 11110, that can be used in this subtraction operation. I can work out this problem in another way. This is what you initially do. This is A and Q register. A register initially filled with zeros including sign bit, and Q register contains the dividend value, that is 9, and B register contains the divisor value, that is 2 including sign bit. You have to find the 2's complement for this divisor, that is 11110, and sequence counter value is 4 because I am taking this division operation as 4-bit number. So this is the initially you have to do. Then first operation is you have to shift the A and Q register value. Shifting the left value means you have to remove this 0. So I can write this value here. So this is actual shifting of the A register content. So I remove this value 0 left out. Then I am writing this 40 here and shift this Q register value here. Then I am writing the remaining value, that is 001, and left blank as the Q naught value. So this is called shifting operation, that is shifting of both the A and Q register. Then after shifting operation you have to subtract the A register content minus B register content. That means you have to add the 2's complement number, that means 11110. When you add these two numbers, you can get the value here. That is called A minus B. So A register content can be added with the 2's complement for the divisor. So I can achieve the A minus B. Now I can check the sign bit of the A register contents. This is 1. So I am going to add the I am going to fill the Q0 value as 0. So this is 1 and I am putting 0 here and do the restore operation. Restore operation is nothing but you can add the actual divisor value to this A register content. So this is the actual register value. If you add these two numbers, you have to achieve the restore operation. After adding, you can get the value here. So you can cross check this value. This should be the previous value. We have achieved the restore operation. This is called first cycle. So after first cycle, your sequence counter becomes -1. That means sequence counter becomes 3. So in this way, you have to do the next operation. In next cycle, you have to left out this 0. Then I am going to write the remaining numbers 0, 0, 0, 1, 0, 0, 0, 1, and I shift this 0 here. So I am writing the remaining number. This 0 can be shifted here. So remaining numbers are 0, 1, 0. 0, 1, 0. I am left blank as the Q0 value. So this is the shifting operation. After that, you have to do the A minus B value. So after A minus B value, you can get this result. And this is the 0 value. So you have to add the value 1. Now you no need to do the restore operation because the value is 0. So this is the second iteration. Now the sequence counter value becomes 2. You can to repeat the iteration again. So this 0 can be left out. You can write the remaining value, that is 0, 0, 0, 0. And this 0 can be shifted here. And remaining value is 101. I am putting as Q0 as blank value. Then you have to do the subtraction operation again. So after subtraction operation, you can get the value 11110. So now the value is 1. So you can fill the Q0 value as 0 and do the restore operation. You can get the previous value. So this is the third iteration. Now the sequence counter value becomes 1. You can repeat this operation again. In a fourth iteration, you can remove this 0 again. So I can write the 0000 and shift this 1 here and writing the remaining value 010 and left blank as the Q0 value. So this is the shifting operation. Then after shifting operation, I can do the subtraction operation, that is A minus B. So after doing this A minus B, I can get this value. So I can get the value is 1. So I can fill the Q0 value as 0 and do the restore operation. So after restore operation, I can get the old value, this one. So now the sequence counter value is 0. So 4 iterations are completed. Now you can check the Q register. So this is Q register. Q register contains the value 4 and the A register contains the value 1. So we are going to divide 9 divided by 2. So I am getting the value quotient as 4 and remainder as 1. So in this way you are write your answer in your examination. Now we are able to solve the restore division operation for any given value. You can work out this problem with these different numbers. You can cross check your answer. If you have any query, you can make the comments in the comment section. Thank you.